remember when we did a nice and relaxing topic like tea and looked at how tea leaves would react with the air? Yeah, I remember that. Well, today I researched fractals and chaos theory for 20 minutes. And yeah, I probably should have done this for 20 years instead before talking about it. But anyway, here's what that looked like. Okay, so we'll go with fractals and chaos theory. And obviously, I'm not going to structure or plan this out until I actually start the timer. Okay, 3, 2, 1, let's go. Okay, fractals and chaos theory. What are we gonna research? What are we actually gonna look into? I guess the overview is the best way to start each time, right? Can't go wrong with that. What are fractals? What is chaos theory? And when I ask these questions, the point is to answer with kind of like a short explanation, a short overview of the fundamentals of it, I guess, right? I'm not going to write that down. That's kind of like intuitive, because otherwise you could obviously interpret this as being a very general, very broad question, because arguably that's what I'm researching overall, right? But anyway, so those are the two main questions for the overview. Maybe we want to look into some of the practical applications of fractals and chaos theory. Where are these concepts applied in the real world? I don't know if I want to split it up into fractals and then separately chaos theory, because these could be like very, very closely related concepts. But I do know, I mean, I know that they're very closely related concepts, but I honestly, I'll just leave it like this, but I probably don't need to divide this up. Anything else that I want to structure for now, though? Oh, maybe the history of these concepts, right? Fractals and chaos theory. How did they originate? And maybe like developments over time or something. That seems pretty good. I'm just trying to think back to past ones that I've done, past research blitzes that I've done, to think about if there's anything that I want to learn from those. In terms of my structure, I don't think I can think of anything like that right now. And honestly, I probably should have given that thought before I started the timer. But I think it's fine for now, honestly. Honestly, the overview part, I would expect this to be the bulk of the, like maybe like 2.5 minutes. It's probably going to be like 1 minute, and this is going to be the remaining amount of time. So just because of the fact that the nature of math concepts is that they're going to be very abstract, very esoteric. So yeah, let's just get into this. What are fractals? What are chaos theory? I don't know what sources to use for this. I've mentioned this before, but math concepts on Wikipedia are kind of difficult to research because Wikipedia uses it can use very high level or like very complex and technical notation for a lot of the things that it's talking about. So let's just see if there are other sources, maybe like Stanford Encyclopedia Britannica, something like that. I just want to go to Brilliant, and we're not sponsored by them, so I'm not going there. Britannica, maybe here. Is chaos theory on this page as well? Chaos. It's not. That is surprising, actually. And do they have chaos theory entry here? Oh, they do. Okay, that's interesting. Okay, what? Are you serious? I didn't know Britannica was a subscription website. What the heck? Okay, let's just find chaos theory on a different website. Space.com. Oh, no, Stanford. I think this is good, because chaos theory, from what little I know, is like a borderline philosophical concept as well. You could relate it to some philosophical questions. So fractals. How have I already used up 5 minutes on this? This is not good. Fractals are a class of complex geometric shapes that have a fractal dimension. Yes, okay. And then they're capable of describing many irregularly shaped objects. Okay, so let's just summarize that. Irregularly shaped objects with a fractal dimension. I'm bringing in a little bit of prior knowledge because I do know what fractal dimensions are technically. I believe they're fractional dimensions, as in like instead of like 1.23 dimensional objects and stuff like that. Yeah, and some examples of that are things like irregular, oh my goodness, irregular mountain ranges. I know coastlines as well fall into this, things like that. Okay, the term fractal is coined by Mandelbrot. Okay, I have heard of this man as well. So history of the concept, I'm going to put it under here with Benoit B. Mandelbrot. Okay, and it derived from the Latin word fractus, fragmented or broken. Okay. I'm going to try to keep my notes a little bit shorter for this one as well, so I can cover more ground. Let's see. So there's an animation of Mandelbrot fractal set. I've heard of the Mandelbrot set, but I don't want to get into that just yet at least. Distinct from the simple figures of classical geometry. They're capable of, okay, yeah. So they're different from shapes in classical geometry. Yeah, let's see. Key concepts have been studied for years. There's a snowflake curve, stock market. Fractals possess the property of self-similarity. A self-similar object is one whose components part resemble the whole. Yeah, I do know about this. Scaling symmetry. Wait, okay. Fractal phenomenon can be detected. Yeah, okay. So this is an interesting one. I could put it under here. This isn't necessarily all of them. I think it says many fractals. Yeah, many have it. And what this refers to is the object is self-similar. It is made up of itself, which is weird to wrap your mind around. It is made up of itself, but I'll try to explain it when I'm talking. For now, I don't have time for that, okay? Another key characteristic of a fractal is a mathematical parameter called fractal dimension. Yes, this is the part that I mentioned here, the fractional dimensions. Unlike Euclidean dimension, fractal dimension is generally expressed by a non-integer, mathematical figure with a six-fold symmetry. Wait, what? What is a snowflake curve? Oh, it's this thing. You might have seen this thing before, right? Snowflake curve is what? Is this a mathematical figure with six-fold symmetry, like a natural snowflake? It is self-similar, yeah, right? It follows that each of the four parts consists of four parts that are scaled down versions of the whole. Okay, that would be nothing surprising if the scaling factor were also 4. However, for the snowflake curve, the scaling factor at each stage is 3. Oh my god, what is happening right now? Dimension of the snowflake curve is thus d. Oh my goodness. Key property and an indicator of the complexity of a given figure. Oh my god, I'm trying to wrap my head around this, okay, so I can explain it at least. If it takes like a minute to understand this, I think that's fine, because it seems like an important concept. It is self-similar in that it consists of 3 identical parts. Wait, I need to look at this to understand what they're talking about. Consists of 3 identical parts. Where? Wait, oh, is this the snowflake curve? Wait, okay, let me just search it up. Snowflake curve. Okay, oh, maybe it's just like... okay, let me just try to understand it using the words. Self-similar, it contains 3 identical parts, each of which in turn is made of 4 parts that are exact scaled down versions of the whole. Each of the 4 parts consists of 4 parts that are scaled down versions of the whole. Okay, there would be nothing surprising if the scaling factor were also 4, when the scaling factor at each stage is 3. What does the scaling factor mean? Oh god, what kind of rabbit hole am I going down now? Scaling factor. Let's look this up. Scaling factor in geometry is a number that describes how much a shape has been enlarged or reduced. Okay, so okay, I understand. So it's like the self-similar whole. Okay, I'll explain it while I'm talking. Okay, but basically it means that the number of constituent self-similar parts is not equal to the scaling factor, giving the shape the fractal dimension. And the way you calculate the fractal dimension is the scaling factor, the actual scaling factor, or no, the log of it over log of self-similar parts. That seems to be the case. I'm going to give this a 50% conviction rate, okay? I could be wrong, but that seems to be what I'm getting from this in like 3 minutes of reading, okay? I don't have that much time, so I'm going to try to get into chaos. Let's look at this. So chaos is what? And how is it related to fractals? Let me see. Oh, okay. So fractals are on this page. Just wanted to confirm. But let's see what the overall concept of chaos is. I do have a pre-existing idea of this as well, by the way. So what is chaos theory? And why are we on Stanford Encyclopedia for Philosophy? So the big news about chaos, it is small changes in system can result in very large differences in that system's behavior. Yeah, right. It's known as sensitive dependence. Okay, so small changes in system, big effects. That is the 5-word summary. Sensitive dependence. It's called sensitive dependence in math. Okay, what else? In addition to exhibiting sensitive dependence, chaotic systems possess 2 other properties. They're deterministic and nonlinear. Yes, I remember this from the book. Half of the book that I read a year ago. Deterministic and nonlinear. So what does this mean? Exhibiting these 3 properties and what their philosophical implications might be. So, okay, I think I understand. Wait, in addition to exhibiting sensitive dependence. Okay, turns out sensitive dependence is somewhat old news. So the butterfly effect is part of chaos theory. It's like a thought experiment or whatever you could call it. I'll put it in here, butterfly effect. Deterministic and nonlinear. And, oh, okay, so basically it also said that there are 3 characteristics of a chaotic system. You have sensitive dependence, plus deterministic, plus nonlinear. These are the 3 things that you need for a chaotic system. And then brief history, I'll get back to that in a bit. But what is chaos theory? Wait. Okay, what is it? Oof, my goodness. I'm trying to glean this by scrolling, just catching a few words here and there. Potential problem, faithful model. What are the... Oh... Listen, I just don't have time to read this. I would read this if I just had a few more minutes. Who came up with the idea for this video? Okay, emphasis on unstable rather than stable behavior. What is this talking about? What is this talking about? Theories are cohesive, systematic bodies of knowledge. Okay, I'm gonna use my pre-existing knowledge for most of the chaos theory stuff, okay? For most of, because I and especially, and I can use intuition as well. Because I think I understand each one of these concepts. Wait, I need to look for non-linear though. Non-linear. What does this mean in the context of chaos theory? Wait, what does non-linearity mean? I'm sorry. It's been like 12 months since I read this book. Well, dynamical systems of interest in chaos theory are non-linear, such as the Lorentz model equation for convection and fluids. I've heard of this. The Lorentz equation. I don't even know if I'm going to include this in the talking, but whatever. Non-linearity, whatever. Dynamical system is characterized as linear and non-linear. Okay, depending on the nature of the equations of motion describing the target system. Oh my goodness. Okay, I have to turn my calculus brain on, okay? Differential equation system for a set of variables. Okay, these variables might represent positions, momenta, chemical concentrations, are solutions of the equation system. If the system of equations is linear, it can easily be shown that x3 of t equals ax1 of t plus bx2 of t is also a solution, where a and b are constant. This is known as the principle of linear superposition. So the matrix of coefficients f does not contain any of the variables x or functions of them, then the principle of linear superposition holds. Matrix of coefficients f does not contain any of the variables x or functions of them. If the principle of linear superposition holds, then roughly a system behaves linearly. Any multiplicative change in a variable by factor alpha implies a multiplicative or proportional change by its output alpha. For example, you start with your stereo at low volume and turn the volume control 1 unit, the volume increases by 1 unit. You now turn the control 2 units. Oh my god, okay. In a non-linear system, linear superposition fails, and the system need not change proportionally to the change in a variable. Okay, I think I kind of get this. You turn your volume control too far, the volume may not increase, by whistles and various other distortions occur in the sound. Okay. Oh my god. I'm just going to type random words here that will help me remember what I just read. So it's like proportionality, multi-dimensionalism. I'll figure it out, okay? I don't even know if I have time for history. I'll probably have to like erase this. Okay, wait, let me just get some practical applications. Practical applications. It said something about the stock market, right? Wait, okay. Do I have to rely on AI for this one? I don't want to, but let's see. Practical applications of chaos theory. Wait, why are they even related? Fractals. Wait, where was the fractal thing? I forgot about that part. Various denizens of chaos, like fractals, actually exist. Wait, what are we talking about? Oh my god, I forgot about this. This is bringing back some of what I read as well. There's no universally accepted definition for strange attractors of fractal dimension among mathematicians. Wait, I need to get a straight answer to this. I don't have time for this. What or how is chaos theory related to fractals? Fractals are infinitely complex objects that are self-similar across all scales. Yeah, chaos theory studies the behavior of dynamical systems, and when a system is chaotic, the curves representing different regions are highly irregular fractals. Studies the behavior of dynamical systems. Okay, I think I got it. I think it's coming back to me. Let me just type this down. I don't even know if I have time for this, though. I don't even know where I would type this. I didn't put this down anywhere. I'll just type it over here. Chaos theory systems develop in the shape of fractals. Oh my god. Okay, I'm getting some idea of like stock market for practical applications and chaos theory. Stocks. I don't have time for this. What else? Practical applications of fractals and chaos theory. Listen, I'm just getting a lot of information right now. I'm putting it together in my brain, and you'll see how this comes together, okay? You'll see. It'll come together. Surely. It'll come together. Wait, why am I reading an article and I have 50 seconds on the clock? What are some... Oh, my God. AI, where are you when I need you? What? Come on. Okay. I know some off the top of my mind. I'll just draw on those, I guess. I think I know this. I think I know. Oh god, stocks and I think weather is one of them as well. Okay. Oh, for this one I'll put coastline. Okay, you'll understand eventually. History of chaos theory. Wait, come on, please. Where's? I just want to know one guy. Lawrence. I got it. Edward Lawrence. I'm not even going to type it down, okay? Edward Lawrence. I have his name somewhere. But yeah, anyway. That was hard, okay? That was hard. And I think I at least have enough, maybe, to talk for 5 minutes. can't go terribly, right? Surely can't be that bad. Look, I have like a full notepad. Come on. Like, it doesn't matter that I can't read half of it. Listen, to be honest though, I did put together a lot of this in my mind, so I think I should be able to talk for 5 minutes. Honestly, most of the time I actually run out of time, so talking for that long shouldn't be the problem. Okay, let's head over to the other scene now. This might be the hardest one so far, but I think if I keep the structure in my mind, I think it shouldn't be that bad. Okay, 3, 2, 1. All right, I researched fractals today. Oh no, not just fractals. Fractals and chaos theory, but they're very closely related concepts. This is the first thing I'm going to tell you. 20 minutes of research is not enough to wrap your mind around the totality of these concepts, but I have a brief understanding now and using some intuitive understanding that I've gotten in the past. So fractals and chaos theory, I'll go over what these concepts are, and I'll talk a little bit about what their practical applications are as well. Okay, so fractals, first of all, these are geometric structures that are not like shapes in classical geometry, mainly because they are self-similar and they have scaling symmetry. These are the two unique features of fractals. Scaling symmetry means that as you resize an object, it remains symmetrical with the original object, and being self-similar means that the object can be broken up into different parts, and each of those parts is actually the same as the original, meaning like the shape is actually made up of itself. And for that reason, you actually have like a lot of fractals that are actually infinitely scalable, meaning you can like zoom in on them on any individual region, and as you zoom in, you'll realize like that individual area is the same as the overall big shape, and then so because of that you can keep zooming in forever and ever. So brief understanding of fractals. Chaos theory is basically the theory that you have systems where small changes can lead to very big changes. Systems that evolve according to chaos theory have 3 important features. They have sensitive dependence, determinism, and they are nonlinear. So sensitive dependence is that idea that small changes lead to big changes. Deterministic means that if you have the initial conditions in a system, you can calculate the future conditions, or like what the outcome of that system is going to be. That's what determinism means, like that the outcome does follow from the initial conditions. And also chaos theory systems are nonlinear. What that means is if you have a linear system, like the different factors that go into affecting that system, like if you have weather or something and the probability of it raining, maybe one of the factors is going to be the cloud cover, another factor is going to be the temperature. In a linear system, each of these affects the outcome proportionally. So if the temperature increases by 10%, the chance of rain increases by 5% or whatever, right? So it increases in a proportional manner. A nonlinear system does not mean that. It means that a change in one of the factors can have very disproportionate effects on the outcome. So even a tiny change in one of the factors can have completely unpredictable, in a colloquial sense of that word, unpredictable effects on the entire outcome of that system, if that makes sense. So sensitive dependence, deterministic, nonlinearism, these are the 3 main characteristics of chaos theory. And chaos theory and fractals are related because the way that chaos theory systems develop over time is like that shape is actually a fractal. There are these concepts called attractors in chaos theory that listen, this is like a 10% understanding of this concept. I read a book a long time ago about this, okay? But basically it suggests that if you could map out the way that a chaotic system develops, the shape that system creates, it actually ends up being a fractal. So the mathematics of chaotic systems is actually directly related to the math of fractals. So the history of the concept, just very briefly, Benoit B. Mandelbrot, he was the one who came up with the term fractals, and there's a very popular fractal set called the Mandelbrot set named after him. After that, I just wanted to go over the practical applications. A couple of them are, like, for example, with fractals, there are actual real things in the world that resemble fractals, like coastlines and mountain ranges and things like that. If you zoomed in on them, they have like infinite scalability, so they're actually fractals. With chaos theory, you could look at lots of systems that develop in deterministic but sensitively dependent ways, such as the stock market and the weather, things that are like very unpredictable. So that's that. Okay. Oh my God. That was so much to go over. I'm pretty sure I missed something. Oh, I wanted to talk about the log of scaling factor over the log of self-similar parts. Man, okay, I missed one important thing because that was like a big thing that I learned about. I mean, if I had to summarize it, obviously this isn't part of the challenge, but if I had to summarize it, it seems like fractals have fractional dimensions, meaning like they're not one dimensional, 2, 3 dimensional. Fractals are geometric structures that have dimensions that can be between integers. So they can be 1.3 dimensional, 1.4 dimensional. And the way you calculate that dimensionality is you take the log of that fractal scaling factor, meaning the factor at which you have to scale it down or up by to get symmetry, and you divide that by the log of the number of its constituent self-similar parts. And that gives you the dimensionality of a fractal. From what I understand, I could be totally wrong about that. I only read half a book about this a year ago, and I only read about this for 10 minutes, okay? But anyway, I think it was okay. It was a hard topic, okay? You have to give me credit for that. Could have gone a lot worse. So I think it was okay. But anyway, yeah, that's that. I don't know what I'm going to do next, but if you have any ideas, let me know. Take care. Good evening and good afternoon. I'll talk to you next time.